The question is now how to calculate the energy. How to calculate the couple cluster energy. And in principle we could of course do it in, we sort of have seen now two ways of calculating energies with correlated wave functions. The first one would be just like in CI, variationally. And variationally means that we calculate the energy as an expectation value. So we take our couple cluster wave function, the full Hamiltonian of our system, and we divide by the norm. That would then be, if I insert my expansion of the wave function, so get e to the t, r to Fock, I get the Hamiltonian, I get e to the t Fock, divided by the same e to the t r to Fock to the t. Now, as I just mentioned, as soon as I have single and double excitations included in the T, this will generate all possible determinants. Not in the case of CCS, but or in CCD, but as soon as I have CCSD, this is the same as if I would write up the full CI wave function. Because I have all excitations included. I did not include them in all possible ways, but I have all excitations. So this is full CI. And then there's no real point sort of to write it up in this way in the first place. I mean, it's just a rewriting of the full CI wave function. I'm back to the full CI problem and I can't solve it. Variational couple cluster expression, you can write it up, but you don't gain anything. I mean, you end immediately in full CI, which we don't want to do, at least not here now. So the other way to do it is what we learned on Tuesday. Because in matter of blessed perturbation theory, we don't calculate the energy like this. We get the energy by taking the original Schrödinger equation, or at least our perturbation theory version of the equations, and we project against one of the basis states in such a way that the energy term in that equation is isolated. And that's sort of projection by projection. And let's see how that goes. And that means we have to insert our wave function in the first place in the Schrödinger equation. So we have our Hamiltonian, we have our wave function. Let's write it immediately like this. R to Fock is then our energy here at the couple cluster level. Like this. That's our Schrödinger, and we could call it, if you want to, the couple cluster Schrödinger equation. What I mean, it's just the couple cluster wave function inserted in the Schrödinger equation. And now the question is, in which way can I isolate ECC from this equation? I want to reformulate that equation that I have standing ECC is equal to something. Now we can basically do precisely, I mean, you could look at the equation and see multiply the equation from the left against which wave function would I have to project this equation in order to make this equal to 1. I mean, that's a number. So whatever I state, I come from the left, multiply with something. The question is, what do I put in here? Which one is going to give me 1 here? Let's just try in order to make it really like we did on Tuesday. On Tuesday, in order to get the Moeller-Blessed energies, we took each order equation and we projected against our reference state, our 0th order approximation to the state we're looking at. And the 0th order approximation was one of the Slater determinants. And we looked at the ground state, so it was actually the Hartree-Fock, the lowest energy Slater determinant, which is the Hartree-Fock wave function. So we did, this is precisely the same as what you do in Moeller-Blessed perturbation theory. Now if you do that, we get here phi Hartree-Fock h e to the t phi Hartree-Fock. Then we get, I mean this is a number, so I can take that out immediately. E to the t phi Hartree-Fock. Now, what is this? Or what does that do? That's written up there. So Emil?
No, nothing.
Nikolai?
So you make the expansion. So one of them is 1, and then you have the T1 to up to what order you.
Yeah, so I get, the first one is 1, which means I get phi Hartree-Fock times phi Hartree-Fock plus, and then I get phi Hartree-Fock, I get T phi Hartree-Fock and several more terms which are sort of powers of T. But what is that going to give me? If I let T act on Hartree-Fock, I get some excited determinant. But all the determinants are orthogonal. So everything which comes here is 0. This is 1. They're normalized. So this is my Cover-Cluster energy. Let's discuss that issue. E to the t, if I multiply that from the left with e to the minus t, in the first place it just gives me e to the minus t plus t, which is e to the 0th, which is 1.